Crystal Violet Kinetics Lab by Josh Caldry, Ishpreet Kohli, Ryan McLean, and Evan Zeal. Here is a brief description of our procedure. In the lab, we had to make a calibration curve so that when the crystal violet reacted with sodium hydroxide, we could use the absorbances to calculate micromolarity of crystal violet to determine the rate order. In the lab, safety goggles were used whenever working with sodium hydroxide, and the materials were the following: 25 micromolar crystal violet, 0.2 molar sodium hydroxide, distilled water, cuvettes, test tubes, Chem wipes, a test tube rack, a calorimeter, a computer, and a graduated pipette. To make the calibration curve, we measured the absorbance and transmittance of 5 different concentrations of crystal violet: 25, 20, 15, 10, and 5 micromolarity. From this data, we made our calibration curve for the absorbance first concentration. Then we diluted 25 micromolar stock crystal violet with 0.2 molar sodium hydroxide to create 20 micromolar crystal violet. This also started a reaction between crystal violet with sodium hydroxide, so we quickly transferred the solution into a cuvette and collected the absorbance over time. It is important that sodium hydroxide is in excess, so all the crystal violet will eventually get used up. Using the calibration curve, we could then use absorbance data to analyze concentration over time. The concentration over time graphs could then be analyzed to find the reaction order of crystal violet. The first data table shows the volumes used in the dilutions. The milliliters of water and crystal violet were determined by dilution calculations. The equation concentration 1 times volume 1 equals concentration 2 times volume 2 was used. For a sample calculation, we plugged in numbers for calculating how many milliliters of crystal violet we needed to make a 20 micromolarity sample. We can see that 4 milliliters of crystal violet are needed combined with 1 milliliter of water to make a total of 5 milliliters at a 20 micromolarity concentration. This process was repeated with the different concentrations of crystal violet. The next data table shows absorbance versus concentration of crystal violet. This data would be used to create a calibration curve. It is important to note that in this data table, 20 micromolar crystal violet has a reading of 0.713 for absorbance. This value is what was used for the reaction of crystal violet with sodium hydroxide because it is under 1, but not too close, like the 25 micromolar concentration of crystal violet. This graph shows absorbance versus concentration of crystal violet. From this data, we found a best fit line. The equation for this line is absorbance equals 0.0382 multiplied by the concentration of crystal violet. This next data table shows the absorbance and concentration versus time during the reaction of crystal violet with sodium hydroxide. The time in this data table is every 12 seconds to allow the data table to fit the screen. The next graph shows absorbance versus time during the reaction of crystal violet with sodium hydroxide. Once the absorbance values during the reaction were known, the line of best fit from the calibration curve can be used to find the concentration of crystal violet. For a sample calculation, our absorbance, 0.689, was divided by the best fit slope, 0.0382, to calculate concentration of crystal violet when time equaled 0 for our reaction. The calculation indicated that the concentration of crystal violet was 18.04 micromolar at the start of the reaction inside the calorimeter. Once the concentrations of crystal violet were known for the times, it was time to figure out the reaction order of crystal violet. To do this, a concentration of crystal violet versus time graph, a natural log of the concentration of crystal violet versus time graph, and 1 over the concentration of crystal violet versus time graph were created. The most linear graph would represent order, being 1, 2, or 3 respectively. From these graphs, it is seen that the natural log of crystal violet versus time graph was the most linear, therefore representing a reaction order of 1 for the crystal violet. Additionally, the equation for the line of best fit for this line is absorbance equals negative 0.00400 natural log of concentration of crystal violet plus 2.897. This equation is useful to find the pseudo rate constant. From the equation of the line of best fit from the natural log of concentration versus time, the slope determines what the pseudo rate constant is. This is because the negative slope of the equation for the line of best fit equals the pseudo rate constant. Therefore, from this calculation, it is seen that the pseudo rate constant is k star equals 0.00400 seconds to the negative first. The units for this are seconds to the negative first power, since this will ensure that the unit for the rate is micromolar per second. This leads us to the goal of the experiment, the rate law for the reaction. The rate law equals the pseudo rate constant K star times the concentration of Cv to the first power, where K star equals 0.00400 seconds to the negative first. Thank you for watching.